Okay, so I'm going to give you a summary for different types of atomic diffusion mechanism we show you in previous slide. And regarding to the ring mechanism, you know that actually the host atom exchange the location with surrounding atoms simultaneously, right? But we didn't actually have quantitatively description on the divisibility in ring mechanism. But for the number 2 to number 4, we did show you how to estimate the divisibility of the diffusion atoms, right? So regarding to the vacancy mechanism, as we know, the diffusing atom exchange the location with the nearby or surrounding vacancies. So the self-divisibility of this diffusing atom equals to vacancy fraction times the divisibility of a vacancy times the correlation factor F. So based on this, can you can have some idea about its proportion to the exponential term and its exponential negative vacancy formation energy and also the vacancy migration energy divided by KT. And why we focus on exponential term? But as you know, exponential will this function exponential function actually will decay dramatically, right? So the value inside this exponential negative term is quite important. So and also this term is also a temperature dependent term. So that's why we want to focus on this term. And regarding to the interstitial mechanism, so the interesting diffusing atom is a smaller subtle atom, and this subtle atom, this subtle atom only need to overcome the migration energy. So you can write down the expression of divisibility of this subtle atom equals to d0 exponential negative migration enthalpy divided by kT. So exponential term only have a migration energy of this subtle atom. And regarding to the interstitial C mechanism, actually the idea would be a little bit similar with that in the vacancy mechanism, right? Because the self-divisibility of the diffusing atom equals to the fraction of interstitial defect, divisibility of interstitial defect, and correlation factor. And this diffusion mechanism is due to there's a interstitial defect nearby the diffusing atom, so that will allow the divisibility through the interstitial C mechanism. So it's same idea, right? It's a fraction times the divisibility of either vacancy or interstitial defect and times the correlation factor F. So based on these results, if we focus on the exponential term, will be the negative interstitial formation energy and interstitial migration energy. So now my question would be, if the purpose here, if you want to increase the divisibility of your materials, what kind or what types of atomic diffusion mechanism you need to choose, or you choose for increasing the divisibility of your materials. So I want to have a higher divisibility, right? And based on this equation, you know exponential term dominate, right? So I will say this is interstitial divisibility. If we don't consider the diffusion atoms belongs to host atom or the subtle atom, then I will say the divisibility through the interstitial defect would be larger than vacancy 1 and interstitial C1 because the migration energy is lowest one, right? Compared to the vacancy and interstitial C mechanism. But if we only consider the diffusivity of the host atom, what type of diffusion mechanism will increase the diffusivity in your materials, your interesting materials? So I will compare the energy part. I will say the vacancy mechanism will have higher diffusivity of the host atom. Why? Because vacancy formation energy is smaller than interstitial formation energy and migration energy. Migration energy probably migration energy, if you consider the lattice distortion one, probably based on different type of interstitial defect, but this one usually will cause less lattice distortion. So if you consider the anti-evaluation energy part, this term was smaller than this term, so the diffusivity was larger than this one. Okay, so I'm just give you some ideas about the diffusivity between through different mechanisms, which diffusivity will have which diffusivity is higher and which diffusivity is smaller. But now we need to focus or talk more about the vacancy mechanism. Do you remember what's the vacancy mechanism we talked before? A quick review for the definition. The vacancy mechanism actually is we have the host atom, right? The same type of host atom, and this host atom also a diffusing atom. There's a vacancy nearby this diffusing host atom. So as long as there's a vacancy, so this host atom, as long as this host atom have sufficient energy to overcome the energy barrier, so it can make a successful jump into the vacancy, right? So this is the vacancy mechanism we talked before, but in some cases, we dope some dopants at the substitutional site. We call it a solute atom. So in that and also this also is a vacancy mediated mechanism. So how to formulate or modify the diffusivity or formulate the diffusivity of this solute atom? So this is we are going to talk about in this part is the vacancy mechanism, but we did dope some dopant at the substitutional site. Okay, and the dopant considers a solute. So can you formulate the diffusivity of solute atom at the substitutional site, or you call it at the lattice point? In this kind of situation, we call it as a vacancy mediated solute diffusion. Okay, so we have host atom in a white ball, and we have a vacancy here, and solute diffusivity, so means that we dope the dopant or solute atom at the substitutional site. So now, how the solute atoms diffuse through this crystal structure? And the example here we choose is a FCC structure. So how solute atom diffuse through this vacancy mediated diffusion in FCC? So now you will find that before, in the vacancy mediated diffusion mechanism, the only possibility is the host atom exchange the location with the vacancy, right? But now things turn out a little bit different because there are three possible different configuration of atoms can jump in vacancy or exchange the location with a vacancy. So there are three different types of uh, the atoms with different types of configuration, right? But some people will ask, oh, what kind of configuration you are talking about? Because now you drop the solute atom in these materials. So when we talk about the gamma prime is a jump ray, this will be a little bit different, right? We can observe three different types of jump ray. Due to what? Due to the, as you know, the jump ray is related to the bond strength, reduced mass, and migration energy. So when you dope the solute atom at the substitutional site, and if this solute atom want to exchange the location with vacancy, then you will find for sure this gamma prime have its own gamma prime, right? And host atom for sure we also have a jumper rate between the host atom and vacancy will be not would be different with the one we just talked about is a gamma prime SV, right? Because the bond strength and reduced mass are different. So, and also we have the third one, jump array, is what is a host atom, but nearby or surrounding solute or neighboring a solute atom. So here we are going to show you actually there are three jump frequency or jump array need to be considered in this material system. The first one is, as I mentioned, the solute vacancy jump array. And the third one is the one you familiar with is a host vacancy jump array. And the number two is what? Is shown in green is the vacancy is and the host atom neighboring solute jump array. So actually this one and this one, although they are the same, they are host atoms, but due to this atom is nearby the solute atom, so the gamma prime, or you can say the beta, and will be difference or reduced mass will be slightly different with the host atom, right? Because the bond strength for this host atom and this host atom will be different. So you got the number two gamma prime is the vacancy host atom neighboring a solute atom. Okay. So now we need to make a now. So under this situation, you have a solute dope at the substitutional site in FCC structure, and if it is also a vacancy mediated diffusion, so we need to modify we need to derive the diversity of the solute atom, right? So before that, we need to make a very important assumption. We consider there's an attractive interaction between the solute and the vacancy. Attractive interaction means there's a negative binding energy between the solute and the vacancy. Negative binding energy means that they like to bind together to lower the total free energy of the system, because negative binding energy, so that will lead to the decrease of the total free energy of the system. So based on this, it's a negative binding energy, so you can expect the energy term will be smaller, so you got the gamma prime will be higher. So that tells you that solute atom like to jump in vacancy and vacancy like to exchange the location with the vacancy. So the solute atom will jump left, and probably jump to right, jump left to jump to right. So they like to together jump back and forth between the solute and the vacancy. So gamma prime SV will be higher compared to the host atom jump in vacancy one. This one has a higher energy, so you got the gamma prime is smaller, the jump rate decrease. Okay, so now you know the solute, because solute and vacancy have a negative binding energy and they like to jump the solute will jump back and forth like this one. But don't forget, the purpose here is we want to know the divisibility of this solute atom, right? So in order to understand how the solute atom diffuse through these FCC structures, so we need to consider two cases. The first one, the same one actually, is the gamma prime between the host atom and vacancy is smallest one. Okay, because the energy is higher, so the gamma prime is lowest. But we still have the other two gamma prime, right? Between the solute vacancy and the host atom neighboring solute and the vacancy. So for case 1, we assume solute vacancy gamma prime between the solute and vacancy is much larger than the host atom neighboring solute atom and the vacancy. And the slowest one is the gamma prime between the host atom and vacancy. So the case 2, we switch the order. So the gamma prime, the highest one is the gamma prime between the vacancy and the host atom neighboring solute, and then will be much larger than the gamma prime between the solute and the vacancy. And the slowest one also is a gamma prime between the host and the vacancy. So let's discuss the case 1 first. We need to know under this situation, this one is the highest one, then this one, and so is this one. Under these conditions, what's the divisibility of this solute atom? For case 1, also we know there's a strong correlation between the solute and vacancy. Okay? This also implies that the vacancy is binded with solute atom for a relative long period of time. Okay, they exchange the location always, right? And the slowest gamma prime will be the host jump into the vacancy due to the higher activation energy. Okay, even though the solute and vacancy bind for a very relative long time of period, and although the gamma prime is highest, but as you see here, the solute jump to left-handed side and vacancy jump to right-handed side, right? But the solute will jump like a back and forth, right? And this behavior has no contribution to the diffusion. So gamma prime between SV has no contribution to its diffusion. So which jumping process control the divisibility of solute atom in this case 1? So the answer is this one is the gamma prime between the host atom nearby neighboring solute and the vacancy. But I want to show you why. So let's take a look on this figure step by step. So I just remark for case 1, the highest one is between SV, then is the vacancy and host atom neighboring solute, and the slowest one is the host atom and the vacancy. Okay, so I also label the solu and the host atom neighboring solu. I use the this green circle to represent it, and we have a vacancy here. So as you know, the solu and vacancy is like bind together for a long period of time. They always jump together, jumping back and forth, right? Exchange location always. And for example, like probably is after 100 times of jumping process. So this event will happen, right? So the vacancy will exchange with the host atom neighboring solu. So the vacancy will jump here, and the host neighboring solu will jump here. So then the solu and vacancy still continue bind together and jumping and exchange location always. And for certain time, the solu locate here, vacancy is locate here, then the vacancy was changed. So after 100 times of jumping process, so next would be the vacancy exchange with the location with the host atom neighboring solu, right? So the vacancy will become here, and the host neighboring solu will become here. So then it will continue. Solu and vacancy will continue to bind together for a relatively long period of time and jump back and forth, right? So one time the solu will move to jump to here and vacancy jump to here. Okay. So based on these results, you can observe what solu diffuse through these several steps, right? Solu atom diffuse through this FCC structure. Based on this diffusion flow chart, you can observe the solu vacancy can consider a pack or a pair. Packed together, they always bind together and moving together due to this negative binding energy. And the way to allow this pack moving or diffuse from here to here is what? Is the jumping process between the host enabling solu jump into the vacancy due to this gamma prong. Okay, so let's try to formulate the. Don't forget our purpose actually is want to get the diffusivity of the solu. But first of all, you need to know the diffusion mechanism for this solu would be what? Would be limited by this kind of jumping process. So the limited probability would be limited by the jumping process between the vacancy and the host enabling solu. So the D as binding with vacancy, diffusivity for this pack is proportional with this kind of gamma prong. And the alpha A actually is related to we call a geometry factor, is related to the different crystal structure, will be a constant depending on what kind of crystal structure we talk about. And so now you know the diffusivity of this solu vacancy pack. So the diffusivity of a solu equals to the diffusivity of a solu binding with vacancy. Okay, so here we also call it this diffusivity of solu vacancy pack times what? This is the diffusivity of solu vacancy pack, right? But this diffusion need to happen because for sure you need to have related to the probability to finding this vacancy solu pack, right? So the probability is quite important, right? same idea as the XV and XI is important for vacancy mediated and interstitial C mechanism, right? So the probability to finding the vacancy solute pack equals to PV equivalent conditions. And this is a probability to finding the vacancy solute pack. So some people probably will directly write down as exponential vacancy formation energy and also plus a vacancy binding energy of vacancy binded with the solute is a PV equivalent, right? But a little bit different is we need to times the 12 here. Some people ask about why we need to times 12. Here I'm giving you I want to explain some more because the solute vacancy consider a pack. That means solute and vacancy they will exchange the location very fast, right? Due to the gamma prime SV is much larger than others. They always exchange the location. So if you put the solute at the center, then there's a 12. The coordination number of FCC is 12, right? That means the vacancy can show up at the nearest 12 locations nearby the solute atom. And at that 12 positions or locations, the solute and vacancy always under that situation, solute and vacancy they will exchange location very fast. So the vacancy can show up at 12 possible locations. As long as it show up, then the host atom neighboring solute can very fast exchange with or jump in this vacancy to allow this diffusion has happened or drive this diffusion happen. So this we need to 10 times 12. Okay? The reason for that is because they exchange the location very fast. But some people probably will ask, Professor, in the vacancy mediated diffusion mechanism, we didn't times 12. Why? In that vacancy mediated case, let me grab the figures. For that one, we only have vacancy, right? Vacancy here, right? So the neighboring atom can only exchange the location with this vacancy, just one vacancy. There are no other chance. But for the one we just talked about, due to the vacancy can show up at 12 different locations due to the exchange location very fast. So this is why this increase the probability to allow the solute to diffuse. So we need to times 12. Okay. So this is the solute, the diffusivity of the solute atom. Okay, so today we ended here.